today. Welcome. So last time we started on energy of a system, and if my memory serves me correctly, we did the definition of work. Work is force times the displacement that the force moves through. And we need to take into account angles, so we say F dot D rather than F times D. It's F dot D, it's a dot product. We did some examples of that. We learned a little bit more about dot products. And then we did, well, okay, let's say that the force is not a constant force. Okay, so then I'll put them in line with each other to make at least that aspect of things simpler. So now I have a force in line with its displacement, but as the displacement takes place, the magnitude of the force changes. And so I'm doing area under the graph, and I can do it like this, which is basically dividing that area up into rectangles and triangles and trapezoids, whatever you want. And I suppose I could have negative pointing forces, and that's one of the things that people need to. One of the problems with this is people will tend to take the thing to the bottom of the page, which is a bit arbitrary. Unless as in this case, the bottom of my graph is at 0 newtons, but that's assuming only positive pointing forces. Supposing I had some negative pointing forces, and then that graph would go below the negative, and people will still go to the bottom of the page, and that's just not thinking it through. It's to the axis. We say below the graph, but it means to the axis when we say that. So watch out for that. And then if I give you an equation for it, and you've got to integrate, then actually people actually do this better than they do the previous example, because they're just more recently they've been schooled in this. And then we got to about here, and we said, okay, let's talk about a thing called kinetic energy. We're going to talk about kinetic energy, we're going to talk about gravitational potential energy, and we're going to talk about elastic potential energy. And we should be just about through then, yeah, okay. And then next time we're going to use these energies. So we're going to talk about this family of energies called mechanical energy. And in the book, every book has different symbols for this. And frankly, in my teaching, if you look at different notes from different times, they're different. Try to let go of what the actual letter, try not to recognize, oh, that letter means such and such, and look at context. So I can say mechanical energy equals the sum of my kinetic energy and my gravitational potential energy. I suppose I'll call that GPE, and my spring potential energy. And basically, if I don't have any springs, there's no spring potential energy in it. If I'm on a flat surface, there's no gravitational potential energy in it. It's just, whatever I have. And so sometimes, these days, they like to only use one letter. So they think they'd write this as, that is equal to K, and that would be U, and I think some people would even call that S, and I just, I still prefer. So anyway, just look at the letters, okay? So this first thing is a derivation, and there's 3 derivations, and it's good to see derivations, although you're not responsible for the derivation. What you're responsible for is knowing the equation at the end. But it's kind of interesting to see how engineering progresses, physics and engineering progresses. And so what we're imagining is a physical situation where we have a block and we have a certain applied force, the blue applied force there. And then what happens is, because of this applied force, we have a change of position, displacement, delta D. And, well, applied forces, unless there's a balancing force, cause acceleration. So I'd expect an initial velocity for my block and a final velocity for my block. Okay, so I can say the kinetic energy, UK, U meaning energy, K meaning kinetic, is the energy that an object has due to its velocity. Change in kinetic energy, delta UK, causes a change in the velocity of an object from one speed to another speed, and is equal to the work required. So work done equals change in energy. Change in kinetic energy in this case, because there's no hill and there's no springs. In the general term, it would be change in mechanical energy. Okay, so let's keep it simple. Recalling that work is equal to the integral of fx dx and F equals ma, you substitute these guys together. So the work done by the applied force is equal to the force applied times its displacement. And the force applied equals ma, so that's going to be ma times your displacement. And then we recall from our kinematics that Vf squared equals Vi squared plus 2a. We said delta x, but delta d is the same thing. And then we say, well, A delta D, let's get that together. Well, A delta D, if we take this 2 to the other side, is a half Vf squared plus a half Vi squared. So just substitute it in. So we're going to say, okay, well, work applied is equal to M times a half Vf squared minus M times a half Vi squared. I've got a issue there. There's an issue. There's a mistake. That should be a negative sign in there. Yeah. Take that to the other side becomes a negative. Yeah. So I know that because this has to be negative down here. And so then along came some smart person who said, why don't we call this kinetic energy? We'll just invent this term kinetic energy. So we have kinetic energy final minus kinetic energy initial. So really what I should say is that my work is equal to my change in my UK or my kinetic energy or whatever you want to call it. Here I'm calling it K. I'm sorry about that. I've got to go through and just clean these up. This is, I'm going to call this UK, if you like, UK. And it's defined as a half mv squared. It's defined as that. Now, and work equals the change in my kinetic energy, delta UK. And that's called my work kinetic energy theorem. And there's a tendency for people to think that there's only a work kinetic energy theorem. And there's not. There's a work mechanical energy theorem, but if all you've got is kinetic, then that mechanical energy is simply kinetic energy. You could have a work potential energy theorem if it's only potential energy. You could have a work spring potential energy theorem if you wanted. But so this is a derivation that's there to define kinetic energy. It's not there to elaborate this law. We decided they were equal to each other at the very beginning, so we're not deriving the fact that they're equal to each other. We're kind of saying, oh, this is kinetic energy. Let's define it. K is measured in joules, and K is a scalar quantity, so it doesn't point in any direction. You know, it's just a value. It's energy storage. The work you do by a force is equal to the energy stored on the object that force is applied to. There is a little bit of an issue, and I want to... I don't want to set the cat among the pigeons, but I want to forewarn you a little bit. So I have an object, and it's got a certain velocity. It's got a mass and a certain velocity. So its kinetic energy, UK, if you like, is equal to 1/2 mv squared. And there's a bit of a problem with that. It's a bit subtle, but I want you to see it because it's going to bite us a little bit later. And that is that velocity is relative to something. Velocities are relative measures. They're not absolute measures. Accelerations are absolute measures. You can feel it in your stomach. If you're accelerating, you can feel it. You can't feel velocity. You can feel change in velocity, which is an acceleration, but you don't feel velocity. I could measure the speed of a car relative to the road, ignoring the fact that the Earth is spinning at about 1,000 miles an hour on its equator. So if I measure the velocity of the car relative to an axis through the center of the Earth, then it's whatever speed it is, either plus 1,000 miles an hour or minus 1,000 miles an hour. So does its kinetic energy change because my measuring situation changed? Well, you'd think it would. And I could measure that velocity relative to the center of the solar system, middle of the sun, be a different number. Measure the center of the galaxy, be a different number. So hold on, this kinetic energy number is like really wacky. So what are we really measuring? We're really measuring a change in kinetic energy. Kinetic energy relative to something. The kinetic energy of that car is so and so relative to the road. But we forget to say relative to the road. So we've got to watch out for that. People don't notice it so much until they get to potential energy, which is next. Gravitational potential energy, and then they start getting concerned about it. What do you need to know? UK, or K, is defined as a half mv squared, and work done is equal to the change in mechanical energy, and if I only have kinetic part of it, then it's the change in kinetic energy. If there's no hills, no springs, it's just going to manifest itself as a change in speed. So horizontal force of 7 newtons pointing to the right accelerates at 5 kilogram, a 5 kilogram block from rest to the right through a distance of 9 meters along a smooth level surface. What is the block speed at the end of this journey? So let's have a look. So it's a 7 Newton force. So I put the forces like in line with the motion. I'll put the velocities and the accelerations above or below, but I'll put my force like almost like a piece of string pulling on the block. 5 kilogram block. I put my masses inside the block, and then at rest, so VI equals 0 meters per second. Let's put a little arrow for it. And through a displacement of 9 meters, so there's my delta x, is equal to 9 meters along a smooth level path. What is the block speed at the end of the journey? So here's my 5 meters. I'm 9 meters further on. I've got a 7 Newton force acting all the way through it, 777 all the way through. And I want to know my VF is equal to, I don't know what that is, meters per second. It's tempting to see this as a kinematics problem. You know, VF equals VI plus AT and all that kind of stuff. And we can actually have a go at it like that. But let's just start off and try and just use our latest tool in our toolbox, which is that the work is equal to my change in my kinetic energy, UK I suppose I should say. So my work is equal to UK final minus UK initial, and I want to know the speed at the end. So what I can say is that my work is equal to, let's actually spell it out, F times delta X. I call it D in the previous bit, but we all know what it means. Is equal to UK final minus UK initial. And so I say, well, plus 7, because it's pointing to the right, times plus 9, because it's pointing to the right, is equal to 1/2 mv final squared minus 1/2 mv initial squared. So 7 9s are 63. 63 is equal to 1/2 times 5 v final squared minus 1/2 times 5 times 0 squared. That goes away. So that means that VF squared is equal to 2 times 63 over 5, if I did that right. So that's going to equal, let's have a look, 126. That's 1,260 divided by 2, which is, get my calculator. I'm getting too old for this. So that's going to be 2 times 63, enter, divided by 5, enter. 25.2. So that means that second square root second answer, my VF is 5.02. VF is equal to the square root of 25.2, which equals 5.02 meters per second, not forgetting my my units. So there we have it. Not bad. Could I have done it using F equals ma? Yes. Let's just prove that. So I can say, well, let's have a look. Vf squared equals Vi squared plus 2a delta x. So Vf squared equals 0 squared plus 2 times a times plus 9. So Vf squared is equal to 18 times a. Oh, if only I had a. And I say, well, F is equal to ma. So a is equal to F over m, which equals 7 over 5, which equals 1.4 meters per second squared. Oh, let's substitute that in and see what we get. Vf squared equals 18 times 1.4, which equals 18 times 1.4 equals 25.2. So Vf is equal to the square root of 25.2, which equals 5.02 meters per second. So same answer. So I suspect that people feel more comfortable with this left-hand side, right-hand side than they do with the left-hand side, but that's just because you've been doing it for longer. And B1. So if I was in your seat, I would have turned around and said, oh, no need to learn this bit then. And then at the test, I would have been really frustrated because as a teacher, we can just miss out information, which makes it impossible or very hard for you to do it using kinematics. I can just lump things together and give you not the initial velocity, but I could give you the initial potential energy, kinetic energy. Boom. And then you've got to unravel that. But if you're just using this side, if I give you the initial kinetic energy, this becomes even simpler. It's like, so watch out. Don't. Everything in your toolbox, it starts off easy. You get 2 tools and you know how to work them. Now you've probably got, if you regard each equation or principle as a tool, now you've probably got 15, 20 tools in your toolbox. And if you're going to be a good engineer, you'll know how to use each one and when. And if you're going to be a kind of so-so engineer, you'll know some of them, not all of them. So some jobs you'll struggle with, and other jobs you'll do well, but you might not be able to do some things. So everything in the book is there because it makes you stronger, makes you a more valuable member of the community. Gravitational potential energy. So, okay, let's look at our physical situation. We have a mass, and that's got a downwards weight because it's in a gravitational field. Let's have a look. I'm going to have a lifting force, an applied force, and it's not going to be significantly bigger. I'm just going to try and balance the weight. Now I'm going to do a little bit more so I move upwards, okay? I mean, I've got to have a little bit more else I won't go anywhere, but I don't want to accelerate noticeably. So this might take an hour for this journey, because we're looking in principle. It's going to go upwards, and we call it delta R in this case. And basically, I have a starting height and an ending height. And I say, well, okay, the energy that an object has due to its position in a gravitational field is called gravitational potential energy, that's UG. The change in gravitational potential energy, my delta UG, caused by moving a mass from one location to another, is equal to the work required. Work is equal to my change in, not potential and not kinetic energy this time, but my change in gravitational potential energy this time. Because there's no velocity to speak of. This will take hours for this to happen. And there's no springs. So the changes in gravitational potential energy. So I say, well, hold on, I remember this. Work is equal to the integral of fx dx, and Fg, my gravitational force, is equal to the weight is equal to mg. So then I say, well, my applied work is equal to the force times the displacement. F applied is upwards, and my displacement is upwards. So F applied times delta R. Well, F applied is the same as mg, because we're basically in equilibrium. So that would be mg times my final height minus my initial height. And so work applied is equal to mgyf minus mgyi. And I can define my gravitational potential energy at any given point as mg times y. Work applied equals ug final minus ug initial, the gravitational potential energy final minus gravitational potential initial. And so I can say that work applied equals my change in my gravitational potential energy. I call that the WU theorem, WUG I suppose it should be. And U is measured in joules because it's energy, and U is a scalar quantity, it doesn't have a direction. And again, so this is where people first notice this issue, because what they say is I go from the floor to the table, and you learned MGH. Didn't you learn MGH when you were first starting MGH? And then somebody says, supposing I dig a hole, so now the floor's not the floor can go, you go deeper than the floor. Does that mean to say that the energy of this box on the table, does it have more energy because I dig a hole underneath it? And yeah, it shouldn't, but it seems like it has. And so, it depends where I'm measuring from. So it's a relative position as opposed to an absolute position. Just like for the car, we had a relative velocity as opposed to an absolute velocity. I should say the height's relative to the floor, but I forget to do that. I kind of ignore that. So then you get to the stage where you say, well, maybe I can find the absolute bottom of the universe. This is where it gets a bit scary. So you dig down to the middle of the earth, and I say, I'll measure zero from there. So if I want to measure the change in potential energy and going from the floor to the table, I take into account that difference in height. But I don't pretend that the height is but if I want the absolute value, universal absolute value, I'll go from the middle of the earth, But then you go, well, hold on, I can fall into the sun. Well, the middle of the sun then. But you can fall into the middle of the galaxy. Well, the middle of the galaxy then. Well, our galaxy is part of a local group, so middle of the local group. Well, our local group is part of a wall that is part of the universe. Well, middle of the universe. I have no idea where the middle of the universe is. It's a real conundrum. Where do you start measuring from? It's a real problem. Because you can't, it's not that we don't know yet, it's that we're probably never going to know where the lowest point in the universe is. It's unfathomable. And so that stymies us for absolute values, not for differences. Differences are a piece of cake. It's the absolute value is a real issue. And we like to think we got the absolute value, It's like, and there's a clever solution to it. And that is, rather than measuring from the lowest point in the universe and using positive numbers as we go upwards, rather than having our ruler start here at the lowest point in the universe and go upwards, why don't we start at the highest point in the universe and have negative numbers that go downwards? So this is 0, and this is 10, and this is 20. And let's say up here was 50. We'd say that's 0, that's minus 10, that's minus 20, that's minus 50. And that feels really uncomfortable, because talking about a negative energy, kind of like, what is a negative energy? But you just simply took your ruler, your positive negative ruler, and you slid it to a convenient starting point. Notice that in both cases, if I go from plus 30 to plus 40, I went up by 10, positive 10. Notice if I go from minus 30 to minus 20, I went up by positive 10. So for differences, it doesn't matter whether you're dealing about going upwards in a positive going line or going upwards in a decreasing negative line. It's the same difference in value. And that takes a little bit of just accepting, playing with. So if I was to talk to you about the absolute value of the gravitational potential energy of this box at this tabletop, it should be a negative value. Because up there is 0 joules, and we've gone in a negative direction from that. Where is the top of the universe? If you're significantly far away from any mass, so interstellar space, close enough. There's lots of places where you're as high as you can effectively be. Because as you go further and further away from the planet, its pull is less and less on you. And yet these bits where there's no difference in the pull on you. If I go from here to here, there's no difference in the pull on me because that planet is so far away. So it's like free motion. There's no additional force in going further away because it's so slight a pull of gravity. That's easy to get to. Chemists use the same idea for when they look at, how many people done chemistry? How many people got to do chemistry? Yeah, so you'll see it when they do chemistry and they want to talk about the energy level of electron allowed states in an atom. They can't measure from the middle, so they measure from the outside. And it's like minus 13.6 eV for a hydrogen atom and all that kind of stuff. It's a negative number because you're measuring from the outside downwards. And it works. It works fine. So I don't want you to not tell you about it and then find that you really get caught up in it and it's really confusing. So be warned. There's just for absolute values, it's a little bit more subtle. And that will keep coming up with us. So a 6 kilogram mass is lifted from a position that is 2 meters above the table. So let's have a look. Here's my table. Here's my mass. This is 6 and that is 2 meters. Position to a position that is 7 meters above the table. What is the change in gravitational potential energy? The work done is equal to delta UG. So my F times, I'm going to still use D because it's just, remember it, is equal to UG final minus UG initial. What is the change in gravitational potential? Oh, that's what I want. So FD, I'm going to go back in circle, is equal to delta UG. So delta UG is going to equal my force. And my force is going to equal, well, let's have a look. If that's 60 newtons, then that force equals 60 newtons. So 60 times my D, and my D is 7 minus 2. So delta UG is equal to 5 times 60, which is 300 joules. Hopefully that's there. Yeah, good. So just words to wise, for those who came in a little bit, probably right on the bell or just a little bit afterwards, I was saying that I just thought I'd graded your papers, so I just forgot all about them. I was sat there comfortably this weekend and didn't even look at them. And then this morning when I realised, it was like, oh man, let's get on with this. So what's on my mind now is, if you're not doing diagrams and you're not getting the answers right, you got to start doing diagrams. If you're getting the answers wrong, if you're getting the answers right, then okay, I'm still a bit uncomfortable with it, but you're not paying a price for it as yet. But if you're getting the answers wrong and you're not doing diagrams, you got to practice doing diagrams. My advice, if you want to be successful in this, is draw diagrams. That's my advice. I've been through this. You need to draw diagrams. I don't know if I told you, one of my old students emailed me and said that in one of his classes he got extra points because his diagrams were so good. On a test, he got extra credit for the diagrams. The professor liked the fact he was drawing diagrams. He was using a protractor, a straight edge with a ruler, and you're getting the angles right. And it's valued because you're more powerful. So do that. And then secondly, answer the question that is asked. On a number of the questions, I noticed people answered the question that was the example I gave, even though I was asking for something much simpler. And if you don't answer the question that's asked, you're not going to get credit. It's kind of like you've got to answer the question that's asked. It's kind of, you can't just come in and sort of say, well, the answer's 75, but I'm not asking you that. Well, the answer's 75, yeah. You've got to answer the question that's asked. So be careful about that. Don't go into autopilot. Don't kind of say, oh, I remember this, because I'm not always going to ask you. In fact, mostly I don't ask you exactly what I asked you in class, so watch out for that. Last one. This is a little bit more complicated, but not much. It's the same approach. We have a spring, not one of the springs like you use in the lab where you crunch them into each other, like a car spring where you can compress it and it doesn't squish up too much, and you can stretch it and it doesn't break. So the way I like to view this is we have a flat frictionless table, we have a mass, and we have a spring. And basically, we're going to stretch it sometimes, we'll compress it sometimes. So I'm looking over here at these diagrams, and what I notice is that when my displacement is in a positive direction, the restoring force, not the applied force, because this is about the spring. The spring doesn't know of the applied force, it just reacts to it. The restoring force, the bit that's in the spring, is pointing in a negative direction. And if I squish the thing up by putting a negative displacement on this, then the restoring force is in a positive direction. So they're always opposing each other. Positive displacement causes a negative restoring force. Negative displacement causes a positive restoring force. That's one thing to realize. And then the other thing that's makes springs interesting is that they don't follow the same kind of force law that gravity does. As we'll see later, gravity follows an inverse square law. If I double my distance from the Earth, from the center of the Earth, I get 1/4 the pull of gravity. If I 3 times my distance from the center of the Earth, I get 1/9. It follows an inverse square law. Springs actually follow a linear law. If I double my displacement, I get twice the force. If I triple my displacement, I only get 3 times the force, not 9 times the force, or not 1/9 the force. So in a whole bunch of ways, it's a very contrasting force-displacement relationship. The other reason why we like springs is not just because it's variety in comparison with gravitational fields. It turns out that springs can be described by Hooke's law. This is what we're describing at the moment. And that Hooke's law applies to many, many, many aspects of the physical world. So Hooke's law is applied to can be applied to things like electrostatic force. Electrostatic forces. It can be applied to mechanical systems. It can be applied all over the place. The other thing that is just happenstance is that systems that obey Hooke's law, that oscillate, then display a thing called simple harmonic motion. And simple harmonic motion is, again, it's everywhere. It's very valuable. And so for a whole bunch of reasons, we're kind of interested in springs because they enable us to do some different problems, but also because they lay down some mathematics, which is really valuable. Let's do our derivation. So we say work is equal to the integral of fx dx. And in this case, Fr, the restoring force, is equal to minus k times x minus, because it's in the opposite direction. K, because it's a constant. If I double this, I double that. And delta x is the displacement. So we call this value a k, this numerical value, a spring constant, because it's constant for a given spring. And it's in newtons per meter. And so we look at this and we say, well, our work applied is equal to 1/2 times the maximum kinetic, the maximum displacement times the force. So here's my diagram I'm looking at. This is a force versus position graph, and I've squished this thing up, so I have a negative displacement. It gets to a maximum value. When I first started pushing, the force was not so big, and then when I pushed harder, the force was more, and then when I went further, the force was more, and then when I went further, the force was more, went further, the force was more. So if you said, well, work equals force times displacement, and you said, well, there's my force and there's my displacement, you get the wrong answer, because it's not a constant force, is it? By definition, a spring does not give you a constant force. So it's much more akin to these problems we did back here. There. We have a varying force with displacement. It's just here I made up the variation, whereas here the variation is given you by Hooke's law. So, well, that's a triangle, and I know that a triangle is a half the base times the height. So the area, which is the work done, is a half the base times the height, which is a half the base, and the base is x max, and the height, well, the height is k x max. So I just multiply that out, half k x max squared. Ooh, okay, let's generalize. The spring potential is defined as a half k x squared. That looks a bit like k is defined as a half mv squared. That's the way of remembering it. It's of similar form. Work done equals my change in spring potential if there's no hill to climb and there's no velocity. Notice the pattern, just when you see the pattern. We started off with definition of work, and we had an additional formula, and then we substituted in and we derived. We started off with the definition of work, and we had an additional formula, and we substituted in and derived. We started off with the definition of work, we had additional formula, and we substituted in and derived. So those derivations follow the same pattern. I used to worry about the fact that I'd look at that and say, I could never have come up with that. Yeah, if I had been able to, I would have done stuff that goes into a textbook. You know, most of us don't do anything that goes into a textbook. So don't be cornered by the fact that you can't imagine doing that and getting something this important. But recognize the fact it's just a derivation. They took two things and they put them together and they got something new. So don't worry about the fact I would not have known to say it's a half k x squared. Well, that kind of fell out. But don't be, you know, this is not an afternoon's work by some undergraduate student. This was a development of a logical thinking that took a long time to develop. Insights, but also from the day that that was developed until it's in this form is years of teaching. What typically happens is the scientists doing research develop relationships, and then it's messy, and then over years it gets refined and refined and refined, not changed but refined, and then it gets to a stage where it's understandable and palatable, and it starts making its way into the textbooks. And so I was watching this, so I'm teaching physics too, and we're doing Maxwell's equations. Maxwell was, it's one of those parts of undergraduate physics where people kind of like, in a way, dread it, because it's like mathematically one of the more extreme bits when you're first beginning. It's one of the more extreme bits. And my sense on that is always you nibble away at it, and part of nibbling away at it I want to get my students is that. Pardon? My phone. Oh, an Amber Alert. Oh, I'm going to kick yours all out then for a minute. Okay. Okay, good. Okay. So I was looking at this. So part of what I thought I'd do for the students is put a video up, which is about the biography of Maxwell, just to break it down a little bit. And so there's this professor talking about Maxwell's equations, and he wrote down these things, and I thought, man, I don't remember that. That looks so complicated. And he said this was what Maxwell wrote down. And the announcers go, the interviewers going, that looks so complicated. And he goes, yeah, it really is. And about 20 years later, it had been refined to this, and they were the more familiar equations. And that process of going from the raw idea to where it becomes a lot more smooth and palatable takes time. It's done more by teachers than it is done by the research. The researcher's off doing something else. And you see that time and time again. A good example is chaos theory or fractals and the like. So that was developed maybe 30 years ago now. It revolutionized a whole bunch of engineering and science. It's still not in the textbooks. It's still kind of like, it's still been chewed over. And eventually, it's in specialized courses, but it's not made it into, you think it could be in general physics. I mean, some of the things are quite accessible, but it's not there yet. They're going through that process. So in this case, spring is stretched by 4 meters. So let's visualize. So here's my string. There it is initially. There it is. And that is 4 meters. I'm drawing it to the right. It produces a restoring force. So there's my FR equals, I'm going to put it minus 8 newtons because it's pointing to the left. What is the spring constant? So let's have a look. Spring constant. My spring constant, I'm going to go restoring force is equal to minus K times X. I have an X. I have a restoring force. Yeah. So my K is equal to minus FR over X. That is minus. My FR is minus 8 over X. My X is plus 4, which equals plus 2 newtons for every meter. So the answer would be C, not D. And often if you ask this question, people will put down D because they don't draw a diagram. I'm harping on this, I know, but they don't draw a diagram. They just look up here and say 8 newtons and they substitute it in, and they forget the fact that that's in a negative direction if that's in a positive direction. And so they end up with a negative value. And that's not right. That's wrong. That's like 4 units away from where it should be. You know, negative 2 is not next to positive 2. Negative 2 is in the opposite direction to positive 2. So they're 4 units away from each other. That's a long way away. So be careful on that. Spring is stretched by 4 meters. Spring has a spring constant of 7 newtons per meter. How much work was performed? So we have the spring at equilibrium. Then we have the spring, and it's stretched by 4 meters. So let's just put that there as 4 meters. Spring constant K is equal. Spring constants are always positive. If you get a negative value, you know there's a problem. How much work was performed? So work is equal to the change in my US, which equals 1/2 K X final squared minus 1/2 K X initial squared. Let's have a look. How much work was performed by the string? So that's what I want to find. So this is equal to, and the work done is equal to the force times the displacement. Okay. Oh, be quiet. Go on. So, let's have a look. I can do it here. So this is displacement of 0. So this is going to be 1/2 times 7 times, that's 4 squared minus 1/2 times 7 times 0 squared. Starts off with 0 displacement, ends up with 4 meters displacement, which equals 4 fours are 16, half of 16 is 8, 7 eighths are 56. 56 joules. 56 joules. I'm sorry, over here I was going to go on a different track and say it was the force times the displacement, but of course the force is varying. That's the thing, the force is varying. Cool. So 3 bits. Cool, let's take a brief 5-minute break, and then we'll come back and we'll get started. The next bit's not long at all. So